Alright, so here we are with the 5-4, and then in the middle here we'll go to the 5-5 nodes. The first thing we're going to talk about here is the Midsegment Theorem. So we're going to prove and use properties of triangle midsegments. So first of all, what is a midsegment? A midsegment is a segment that joins the midpoints of two sides of a triangle. So of course here in this diagram we have three of them, but if we just kind of identify this midsegment, usually my mental image of what I'm thinking of is just the one line that's here in the middle. All it's doing is separating the triangle into by a segment that has been found from a midpoint over here and a midpoint over here. Now, of course, if you make all three of them, you actually end up making a triangle that is similar in size to this other one. It's just a little bit smaller. So, interesting to note. But the idea is that we have all of these midsegments, and there's a few properties that we can go over from that. But every triangle has three midsegments, and those form a midsegment triangle. So this is your midsegment triangle inside. The relationship shown in example 1 is true for three midsegments of every triangle. So if we see here in this triangle, it turns out that the two lines that make up kind of the bases, if you would, of this triangle are parallel. So from that, we end up actually having a lot of, for instance, corresponding angles and things like that. So midsegment of a triangle is parallel. So going back to the previous image, this line would then be parallel to this one. This one over here is parallel to this one. The obvious looking parallel ones are in fact parallel based on them being midsegments. The other option about other than parallel is that it's actually half the length. So either if we know the length of this base, we can divide it by half and get the middle, or if we know the length of the middle, we can multiply by 2 and get the base. So parallel and double the length is what we end up getting. So we'll go ahead and use that idea on our next piece here. So we have to find the measure of BD. So here's BD, and we just talked about how that segment is half of this segment, and we know that that segment is 17. So BD is half of AE, and AE is 17. So BD is going to be half of 17, and so BD is going to be 8.5. Alright, same picture, but now they want us to do angle CBD. So angle C to B to D, that's this one here. So in order to find that angle, interesting piece about that is the parallel lines that we have. So there are, of course, lots of sets of parallel lines, but if we take this line, and then this transversal,
for what purpose? For what purpose?
Sorry, I clicked my computer. So here's the two set of parallel lines. Here's the transversal. They're telling us that this angle is 26. And so by alternate interior angles, that angle also has to be 26. So it turns out the measure of angle CBD is equal to the measure of angle FDB. And that's by alternate interior angles. And so we get to say that the measure of angle CBD is 26 degrees. When I was looking at this problem, I did kind of try to do things with this one and this one, but that wasn't leading me over here to this angle. So we end up using the two blue ones that I marked here as being parallel, of course, because it's a midsegment. And then we have our transversal here. All right, so that was the tiny piece of 5-3, which is of course why it was, 5-4, which is why it was abbreviated. And now here's 5-5. So 5-5 talks about these inequalities in triangle lengths. So the angle side relationship in a triangle is given here. If two sides of a triangle are not congruent, then the larger angle is opposite the longer side. So longer side, opposite of it is longer angle. So taking a look at here, if AB is longer, then this angle in its opposite is larger. If BC was smaller, then this one here is going to be smaller than this angle. So opposite angles and sides have this relationship. All right, the other piece, of course, is kind of just the converse of what it is, and so now it's actually just talking about the side lengths themselves. So if we know that an angle, for instance, is larger than another angle, then we know that the side opposite that angle is larger than that side opposite, the other angle. So that's all it is opposite sides and angles have a relation to other sides and angles. If you know one's bigger than the other, either an angle or a segment, then you know the other is as well. So, on that note, the way that I like to think about this, and of course it is not exact, is that if this side is mentioned as 17.2 in length, then I imagine that this side is 17.2, this angle across from it is 17.2 degrees. It helps me do it in a quantity rather than kind of just knowing bigger, middle, and small. So this is not, of course, true. All right, it is not 17.2 degrees, but it does help me kind of understand which thing is bigger than the other. The next piece that I would do is then say that if this side is across from this angle, then this angle is 19.6 degrees, again, or some format of that if I actually put a variable with it. And then the last one down here is opposite to this side, and so I'd say that that one's more like 20.4 degrees. Again, not exactly. In fact, it's mostly proportionate to that, so we'd just put a little x with it. So, looking for writing the angles in order from smallest to largest, that would mean that the angle that has 17 would be the smallest. So the smallest angle is angle F. The medium angle, if you will, is going to be angle H because it's 19-ish. And then the bigger angle is going to be angle G. Again, just reiterating that these are not actually these angles, but it is helping us kind of understand that one is bigger than the other by associating that number with it. All right, the next one here, we're going to write the sides, and of course we're missing one of the angles, and so we have to remember that 180 degrees makes up a triangle, and so if we take out that 72 and 60 that are already mentioned, we end up with 108 minus 60, so 48. So we have 48 degrees happening over here in this corner. And just as I did before, what I'm going to do is take this angle and match it with the side that is opposite it. So I'm going to pretend that this one is 48 in length, but it's not. I'm also going to kind of identify that this side, since it's opposite of 72, is about 72 in length. Again, 72 in proportion to actually being the side length. And then this last one here is 60, and so I'm going to make this side kind of a 60x in association with that. So, the next piece here, when we're writing the sides in order from shortest to longest, would then just be to identify the smallest number. So shortest would be PQ, because it's mentioned as being 48. Then the middle value is going to be 60, so that's QR. And then the largest value is going to be PR. Again, just reiterating that these are not actually the lengths, but they are helpful in understanding which one is going to be largest and smallest in association with its opposite angle. All right, so then we get to the inequality part of this, and so a triangle is formed by three segments. Who knew? But not every set of three segments can form a triangle, because sometimes one of the sides, if you just pick three numbers out of thin air, one of the sides might be too long and wouldn't actually make the other two meet, or maybe it's too short and then the other two wouldn't meet. For instance, taking a look here, if I had a length of 7 and then 3 and 3, because 3 and 3 only add up to be 6, there's no way that those 3 lengths could actually make 7, and so you're going to end up with this kind of holy angle. This one over here, however, notice that that length is 7 for the longest, but then the other two add up to be 8, and so because they add up to be bigger than the longest side initially, we can say that that would actually form a triangle. And so the association that we are looking for here is saying that if you have two sides greater than a third side, we are going to end up with a triangle that is formable. There you go. If you don't have two sides that are bigger than that third side, if you have one that's actually less than is going to mean that you have no triangle that could be formed. Because they're not going to end up meeting, they're not going to be long enough. So one way that I tend to look at this is actually as the Pythagorean theorem. So if we think of it as kind of this A side plus this B side being greater than the C side, you can kind of think of it in terms of a right triangle. Of course, what happens is that this is not right triangles, this is every triangle. But if you think of it as A squared plus B squared is greater than C squared, greater than is going to mean that we have an obtuse triangle. Less than is going to mean that we have an acute triangle. And equal, of course, is going to mean that we have a right triangle that we're looking for. So, taking a look at these sides that are given, again, we don't need to go through every single addition. We can just pick the largest one, which is 19, and see if that is greater than, less than, or equal to the two smaller ones added together. So the two smaller pieces added together are 17, and 17 is less than 19, and so in that case we cannot form a triangle. Because there is no way that 7 and 10, having that 17 inches, is going to end up matching with that 19 inches. They're just going to kind of flop on the ends there. Alright. The lengths of two sides of a triangle are 8 inches and 13 inches, and we need to find the range of possible lengths for the third side. So this is an interesting idea, because now they're saying that now that we know that one of the two sides is 13 and one is 8, what does that mean that we could have for that third side being greater than or less than? So in order to get that third side, what we're going to do is take each number and add them, and then take each number and subtract them, and that is going to be our range. So if we add 8 and 13, we're going to get 21 as the largest length that it could be, because that would kind of mean that it's a line. If you have one length of 21 and then an 8 side and a 13 side, you'd end up having a flat triangle, which is not really a triangle. And then if we subtract them, so 13 minus 8, we're going to end up with 5. And so that's actually going to be the closest that they could possibly be before kind of one lifts off of the other. So 5 is the lower amount that it could be, and 21 is the higher amount it could be, and they can't be equal. As I was just drawing in the previous image, it can't be equal, because if it was equal, then it would be a line, and a line is not a triangle. So got to watch out for that. And then we are just talking about a variable in the middle, so we don't necessarily have that. So if you have an 8-inch side and a 13-inch side, you can have a range between 5 and 21 of the length of the third side that will actually form a triangle. Too much more than that is going to make it not touch, and too little of that is actually going to lift one of the sides as well. So, all right. So those are our ideas of the Midsegment theorem, and then also this inequality idea in a triangle.